Swayam Prabha. Digital India. Educated India.
Welcome back. Today we will start or we'll talk about public key encryption. So everything we talked about yesterday was symmetric key, so symmetric key encryption and authentication in the MAC. We also talked about doing it together, authenticated encryption. And the bottom line from yesterday was that everything can be based on a pseudo-random function or a block cipher. And in theory, in practice, these blocks, this PRF is a block cipher, right? And it's something like AES, which is built, which has some heuristic security. It has withstood all sorts of attacks. People have thrown at it. But in theory, you can actually do a little better. You can build a PRF with some sort of a provable security. Again, we cannot completely prove it's secure because we don't know, for instance, the question of P versus NP, questions from complexity theory. Right? So, based on some assumptions, basic assumptions about computational hardness of some functions, in particular something called one-way functions, we can build a PRF. Okay, so unfortunately, don't think I had time to have a few slides, but I don't think I'll get time to talk about how that construction works. But let me just tell you what a one-way function is. Okay, so one-way function maps. Again, I'm calling it like k bits to n bits. You could think of k bits as a security parameter. There's 128 bits I keep mentioning. So such a function is a one-way function if, first of all, it has to be efficiently computable. On the other, so that's efficiently computable in the forward direction. On the other hand, it should be hard to invert in some sense. In what sense? Here is kind of a more precise notion of what it means to invert. So here is the experiment. We will pick a uniformly random x, v as in the experiment, compute f of x, and give f of x to the adversary. And the adversary's goal in some sense is to find this x, but it's okay if it doesn't find this x, but find some x prime which computes to the same value under f as x. So f of x prime equals f of x. Okay? If it does that, then it wins the game. And to be a one-way function, the probability of any adversary, any feasible adversary being able to do that should be very small, should be negligible. Okay? One thing about one-way functions is that it sounds like from f of x you cannot find this x, right? But that doesn't mean x is completely hidden by f of x. F of x could reveal half of x. Okay, there's no secrecy guarantees about x. It's just guaranteed that you cannot find all of x, or you cannot find some other x prime which all of some other x prime such that f of x prime equals f of x. Okay, so that's what a one-way function is. A very simple definition. There are several candidates for one-way functions based on number theoretic things like factorization. So multiplication would be the function, right? F will be multiplication, and trying to invert f would be to factorize it into its, so say 2 prime factors. And there are many others based on, so we'll see something today later. So there's not just that this is good enough for PRF, but this is necessary. You need, if you are going to have a PRG or a PRF, you need to have a one-way function. Okay, so it's exactly the kind of computational hardness that's needed to build a PRF or a PRG. Okay, so in theory, that's all that's needed. In practice, you don't do it because those constructions are very inefficient, practically speaking. All right, so this looks like a good situation. We know how to encrypt, authenticate. Everything can be built on block ciphers, even though it's a heuristic assumption that block ciphers are a PRF. Seems to be good. However, this comes with a major limitation, and that's about the symmetric key. How do these parties get their key? So Alice wants to talk to Bob using symmetric key cryptography, Alice and Bob need to share this key ahead of time. Okay? And that sounds, so there are two problems with it. One is that Alice wants to talk not just to Bob, to many, many people want to talk to Alice, right? And for each of them, she has to have a key for every one of them, right? Which, in fact, let me put it differently. For every pair of parties, Alice and Bob, there needs to be a key in the system. Okay? That's a lot of keys that people are collectively creating and maintaining. But maybe a more important problem, it's not just about how you store all these keys. You could manage that probably. But the bigger problem is, how do these people get together and agree on keys? Right? So Alice needs to go and talk to this Bob ahead of time, to each of these Bobs she wants to talk to. Somehow ahead of time. She cannot do it over the internet, over this channel that she's trying to secure, because they don't have a key yet. They need that key to securely communicate. So it's a bit of a chicken and egg problem, right? They cannot just pass this key, like they need to both get the same key. So Alice could pick a key and give it to Bob, but she cannot give it to Bob in the clear because she doesn't have encryption yet. Okay, so that's a big problem. You cannot bootstrap this process. Okay, and the solution for that is public key encryption. Okay, of course, people have been using symmetric key encryption for a long time. You have heard of things like CISA cipher, and even though they're very weak, they have the same idea of using a symmetric key encryption scheme. And that's what was used all through World War I, World War II, whatever. And people have been trying to figure out a way to get around this big problem of having to ship your keys to the other end ahead of time. And among other people probably, there's someone called James Ellis. You wouldn't have heard of it. In fact, most of the people wouldn't have heard of him. Just some scientist at this place called GCHQ. It's a British intelligence general communications headquarters. And he had this idea that maybe you could do something where you don't need to share a secret ahead of time. But he didn't know how to do it. So that's what he would like to do. And he, so this is what he wanted to do, right? Instead, everybody would have a public key. So this is talking about encryption. Everybody would have a public key, and so it's a public key. And if you want to send me a message, you just need to know my public key, this one key. So everybody needs to know just this one key. They don't need to individually share a key with me. And only I can decrypt a message that's encrypted using this public key, because I'm the one holding the secret key. Okay? That is the idea. So that's basically public key encryption. But he didn't know how to do it. The question he was asking is, can you do it? And he asked this to people at GCHQ, and among them a mathematician, Clifford Cox. And Cox came up with an idea, which we call RSA encryption today. Okay? So the RSA function, to be more precise. And that was great, but they didn't publish this. It was like a big revelation that it can be done. But GCHQ is a super secretive government agency, so they kept it all classified. Nobody else knew about it. A few years later, again at GCHQ, another mathematician, Malcolm Williamson, came up with another encryption scheme, which we know of as the Diffie-Hellman idea, or the Diffie-Hellman key exchange, if you will. Okay, and that is also not published. But all of this were, after a few years, rediscovered in the open literature. And the people you see here are Merkle, Hellman, and Diffie. So Diffie and Hellman published a paper. Merkle also had similar ideas, was a student of Hellman, about trying to do similar things. Not exactly what Diffie and Hellman did, but other things. And what they discovered, the paper was called New Directions in Cryptography, and it was indeed a milestone, right? It introduces the whole possibility of public key cryptography, which made it really feasible for people to use. Today what we are using over the internet is all because there is public key encryption. And encryption is not the only thing we need. We also need signatures, and that idea was proposed or kind of conceived by Rivers, Shamir, and Adelman at MIT towards the end of late 70s. And they also came up with their own encryption scheme, which they didn't know was what Clifford Cox had invented several years back. But this was all published, right? So they had the RSA encryption scheme, or the RSA function, trapdoor permutation is what I would call it today, and the notion of digital signatures. Okay, and of course, those things by themselves were, they didn't have a definition of security. Things were a little rough on the edges, but that's what kind of still gets used. RSA, Diffie-Hellman, they're all still used. Okay, so that's what we'll see. I should also mention, just right after that, when all these new constructions came about, people were trying to also make sense of, to kind of give proof that these are good, right? Give some mathematical proof under some assumption, but there was no proper definition of what encryption is, what security or secrecy should be. And the first kind of proper definition for that came from Shafi Goldwasser and Silvio Micali. Goldwasser and Micali. They also had an encryption scheme, but I think more importantly, they had the formal definition of security, which is yesterday what we saw, the CPA security, and similarly we'll see today the public key version of it. They're essentially what came from Shafi and Silvio way back. I mean, their definition was called different, was phrased differently, but it's equivalent. Okay? And not surprisingly, this was a big deal, the public key revolution, right? And all of these people have won Turing Awards. Not Merkel, but Diffie and Hellman in 2015, late. And Hellman said, he thinks Merkel also equally deserved it, though it was a paper by Diffie and Hellman that was a milestone. And RSA in 2002, and Goldwasser and Micali 2012. Okay.
So my question is, how does public key solves the problem? Because you said that there is one public key for encryption, and you can encrypt the message, but only the sender can decrypt the message. But the problem remains same. Only the sender is decrypting a message, but we want the receiver to decrypt the message. So how is that?
No, so the question is, how does public key solve the problem that I mentioned about symmetric key encryption? So we'll see that in more detail. But no, the sender has a public key that they have published. They're holding, not the sender, did I say sender? Maybe that's what confused me. The receiver publishes a public key, and they're holding on to the decryption key. And everybody who wants to send it, they look at this public key and create a ciphertext, which only the receiver can decrypt. Sorry if I said that. So here is the definition today first, right, before we see any constructions. So it's very similar to the chosen plain text attacks security. By the way, the IND here stands for indistinguishability, and chosen plain text attack is CPA. So now there's a public key, right? So the key generation algorithm, think of this as the receiver, if you will, okay, who runs the key generation algorithm as well as will be running the decryption algorithm. But in this experiment, actually, they will also be, never mind. I mean, this is just part of the experiment. So right now, it's not important where the key is generated. So the key is generated in the experiment somewhere, and only the public key is given to the adversary. Okay, the public key is meant to be public, so the adversary should see it. So we give it to the adversary first. We also have this bit B here, which we are going to ask the adversary to guess. Okay? And kind of as before, the adversary picks a pair of messages M0, M1. and we will encrypt one of them, M sub B, and give the ciphertext to the adversary. Now, in symmetric key encryption, the version I showed you, there was a loop here. You could do it as many times as the adversary wanted. That's not important here because the adversary has a public key. And, well, that doesn't mean it's the same experiment. But there is an argument you can make to show that, if you are secure according to this definition, which has only one ciphertext being created by the experiment, but the adversary can create any number of ciphertexts they want, then it will be secure against an adversary who can also, in an experiment where the adversary can query the M0, M1 as many times as it wants. Okay? So there's a little simpler definition than what I showed you for the symmetric key encryption version. Because there is a public key, it's easier to write it this way. Okay? But of course, if you want, you can put the loop also. It's an equivalent definition. And there's a non-trivial proof saying those two definitions are equivalent. Okay? But let's go with the simpler definition. So the adversary says one ciphertext, and then it has to guess this B, right? So it outputs a B prime, and the advantage is, probability B prime equal to B minus half, could say the absolute value. I've written here it's less than or equal to nu k, which I didn't use this notation yesterday, just to say that's a negligible function in k being a little k there is supposed to be the security parameter, which I've been brushing under the carpet so far. So this is just saying probability B prime equal to B minus half is very, very small. Right? It's negligible. Okay, so that's the definition. Any questions on the definition? Okay, it looks very similar to the symmetric key encryption situation. The adversary can get a pair of messages encrypted, one of two messages encrypted, and has to guess which one was encrypted. Okay, and again, a deterministic encryption wouldn't have worked. In this case, probably it's easier to see the adversary has a public key, so it can create encryptions itself. So if there are going to be, an encryption of M0, if it was going to be deterministic, it can, encrypt M0 and M1 itself and check whether the ciphertext matches this one or that one. But that's not going to work because the encryption process is randomized. Right? So whatever the adversary gets by encrypting it a few times, even wouldn't look anything like what somebody independently generates by encrypting. Okay. All right. So I had this definition here with this negligible, and by the way, it's for all efficient adversaries. Hope it was mentioned here. Yeah, it says all PPT adversaries, stands for probabilistic polynomial time. Just what I was calling efficient adversaries yesterday. Okay, but why not ask for perfect secrecy? Well, because you cannot get it. Okay. In fact, Shannon already told us that, right? Said the amount of communication you can do is only as much as the amount of key you have already shared. In public key encryption, you have shared 0 bits of key between you, so you can send 0 bits of information with perfect secrecy. So this is just why did Shannon say that? We didn't see a proof or anything. This is just trying to kind of motivate that. Actually, since I'm running short on time, I'll skip through these today. But you should think about this, offline. Why would an information theoretically, computationally unbounded adversary always manage to learn the message? It'll learn the message exactly, if there was no shared key between the sender and the receiver. Okay. Okay, so the bottom line is that you need computational hardness to get public key encryption. Okay, there's one caveat here. If you are working with a channel model where the eavesdropper cannot exactly listen to the message that Alice and Bob are sending, there's a little caveat here that, not caveat, there's a little kind of a feature that's available if the channel has imperfect eavesdropping. And in that case, there are mechanisms, coding schemes, which can get you perfect secrecy, without Alice and Bob having shared anything. It's not a very common situation, right, because we are talking over the internet. But there are specialized scenarios where you could imagine this would work, like if you're using some NFC kind of thing, right, where you are keeping the two devices close to each other and you don't expect an eavesdropper to be that close by. And so they'll get a more noisier kind of message. Then you can do public key encryption or something equivalent to public key encryption without any computational hardness requirements. Okay. But that's a niche kind of question. We'll not worry about that. So for us, we need some computational hardness. Okay. So let me kind of show you one scheme at a very high level. And this is a scheme by Diffie and Hellman in the 70s, right? And they didn't present it as an encryption here. This is in the form of a key exchange. So Alice and Bob want to talk to each other confidentially. They have not shared any key between them ahead of time. Okay? And imagine it's an authenticated channel, so they know they're talking to each other. It's just that it's open. It's an open channel. Everybody can hear what's going on there. So here is an idea. Okay. So somehow the plan is for Alice and Bob to actually generate a secret key. And then they can use that for symmetric key encryption, right? So they want to generate a key that they will both know, but will be hidden from Eve. So it has to be random or pseudo-random. So here is a protocol. So we have our Alice, Bob, Eve. Alice will pick a random X. It's a random number in some range. Doesn't matter for now. So just think of it as some integer in some range. And she will compute this thing, which again, it's not a very formal, I'm not fully told you what that means, but think of it as g as another number, again in some subset, and g to the power x is just raising the number to the power x. Okay? And she will send this x to Bob. And similarly, Bob will pick a random y, a small y, little y, and compute the capital Y in a similar fashion, y equal to g to the y. So this g is supposed to be some publicly known g, right? It's some system parameter that has been set up, so everybody knows the g ahead of time. Okay, so they send these two things. So far, Alice has a secret little x, and Bob has a secret little y, but there is no common secret that they have agreed on. But here is the big idea. Alice can compute this capital Y to the power little x. So what is that? Capital Y is g to the power little y to the power little x. So g to the power y to the power x. So that's just g to the y times x, right? Or g to the xy. And Bob can also compute g to the xy by taking g to the x and raising it to the little y that he has, right? So both parties can compute g to the xy. So now they have something that's shared. What does the eavesdropper see? She sees g to the x and g to the y. And hopefully she'll have no idea what g to the xy is. Okay, g to the xy should be pseudo-random given g to the x and g to the y. If that's the case, then this would work. Okay. So that's basically the idea of Diffie-Hellman key exchange, that you can do this. Now we need to see, when is this last thing going to work, right? Given g to the x and g to the y, maybe you can compute g to the xy, or maybe you can learn something about g to the xy. So we don't want it to be revealed, so we want it to be pseudo-random. Or, what we want is this g to the x, g to the y, and g to the xy, if I give you as a tuple, it looks indistinguishable from g to the x, g to the y, and some completely independent random element, right, r. So if you could say these two distributions, when you pick x and y at random, are computationally indistinguishable. No feasible adversary can have a non-negligible advantage in guessing where the sample came from, then we would be in business. Okay? But is that reasonable to expect? And that depends on where all these things came from. The G, this G came from, right? And what do we mean by G to the power x? So let me kind of take a short detour and talk about groups. Okay? So group is just an abstraction of some mathematical operations that you can do within a set of numbers, set of elements. The elements don't have to be numbers, but you could think of, so okay, here's what a group is, right? There's a set G of elements. For now, think of them as numbers, and some operation star. So now think of that as addition. Okay, and the operation, this addition, has a few properties. It's associative, means A plus B plus C is the same as A plus B plus C. There is an identity element in the group, so it's like 0, and it's invertible. So if there's an A, there's a minus A, so that A plus minus A equals, the identity equals 0. It's a commutative operation, meaning A plus B is same as B plus A. Okay? So these are basic properties you would have always seen for addition, and sometimes even for multiplication, except this invertible, not there for integers, right? But for if you're working with real numbers other than 0, even that invertibility is there. Okay, so that's what a group is. This G. So let me give you a few examples. Okay, so the G can be. So my first example was the group is just of all integers. So there's an infinite group, and the operation is plus. Right? So everything is an inverse. A little more kind of more useful thing for us is our finite groups. Okay, groups which are not infinite, and such a group, an example of such a group is Zn, which simply stands for integers modulo n. Okay, so it's numbers 0, 1, 2, 3 up to n minus 1, and the group operation is addition modulo n. Okay, so you add something, it becomes larger than n, you subtract n from it, and that's addition modulo n. Okay, I hope all of you have seen addition modulo before, right? Okay, so it's not crucial for this lecture actually, even if you haven't, but yeah, it's a very, very useful thing to know. And another example here is that give me any group, so for instance Z2, addition modulo 2, the group has two elements, 0 and 1, and addition is the XOR operation. Okay, and addition is just the XOR operation. Now you could take a group and build another group by just taking the Cartesian product of this group some n times. Okay, so instead of a bit, now you could talk about a bit vector, a vector of bits. So for a bit, the group operation was XOR. For a bit vector, the group operation would be bitwise XOR. You XOR the bits together, so coordinate-wise operation. That would also be a group. Okay, and the identity of the bitwise bit vector group would be the 0 vector. Okay, so the length is fixed, some n here, and the addition is just bitwise XOR, and inverses itself. An element's inverses itself. So that's another example of a group. Okay, just some jargon. I might refer to a prime order group at some point. Order of a group just means the size of the group. Okay, the number of elements in the group. So we'll be interested in finite groups, so we'll have a finite order, and there will be some number. So the addition modulo 2, the order of that group is 2. Okay, addition modulo n, the order of that group is n. We'll also be interested in a special class of groups called cyclic groups. So cyclic groups simply means there is some element, at least one element, such that you can generate every other element by, okay, maybe I should mention one thing before going on. People use two different kind of notations for groups. Sometimes you use an additive notation, so this plus. Sometimes you use a multiplicative notation, right? You would think of the operation as a dot. And if I want to say something like, g plus g plus g, if I'm using the additive notation, I could call it 3g. If I'm using the multiplicative notation, I'll call it g cubed, right? So actually, I'm going to use the multiplicative notation for abstract groups throughout, right? Of course, if I'm working with a particular group, I might mention if it's addition, then I will use addition. But actually, in this lecture throughout, I would be using the multiplicative notation. So when I say g to the power 0, that means the identity element. G to the power 1 is g. G square is g dot g, where dot is a group operation. G cube is g dot g dot g, right? And what we would want is that if you did this operation, if you did this, took this g and multiplied it to itself, by the way, there's a fact that if you multiply it to itself the ordered number of times, you'll get back the identity element. But if you multiply it up to g minus 1, the size of g minus 1, you would have generated all the g elements, starting with the identity element, g to the power 0. Right? So we want all the elements to be generated by this g, by powers of g here. All the elements, so this capital G should be equal to this set. Right? All of these should be distinct. That's what it's saying. If that is the case, if there is a little g of that kind, then we call it a cyclic group. Okay? So just to make it look like a cycle, here is an illustration. So by the way, a prototype for a cyclic group is addition modulo n. Prototype meaning there's an isomorphism. So where, yeah, never mind. So you could think of this cyclic group as all the elements sitting in a big cycle, and so you start with the identity element at the top, you multiply by g, you move one clockwise, right? And when you have g to the, here it's called n minus 1, you multiply it by g once, you will get g to the power n, which is the identity element. So that will always be the case, g to the power n will be the identity element, but what's important here is that you will not hit the identity element before that. Okay, that's what a cyclic group entails. Okay, and addition modulo n, this g to the power 0 is 0, g to the power 1 is g, which is 1, g square is 2, g cube is 3, and so forth. Right? Because g cube just means 1 plus 1 plus 1. Well, that's one of the generators. There are other generators. There are anything which is co-prime with this order of the group is a generator.